Good day, and welcome to Africa Teen Geeks. This is the STEM Digital School. If you have just joined into this classroom, you are on the grade 11 Physical Sciences. Okay, my name is Nonkulilego Matondo. I am your Physical Sciences grade 11 teacher. It is the 17th of July 2020. It's a Friday, yes, and I hope that everybody is in a good mood from some physical sciences and applying the Coulombs Law. Remember before, guys, last week or since we started doing this chapter, we did all the theory part of it, okay? And the only thing that we know at the moment, according to the amendments of the ATP of the CAPS syllabus, is that for this chapter, for the whole electricity and magnetism, the electromagnetism is the only unit where the calculations have been removed, but we have to do the calculations for all the other ones, okay? So today we're going to be doing the application of the Coulombs Law. Like I mentioned already, we've already done all the theory part and we did also the revision of the theory part. So now we're going back and we're doing the calculations and we're going to be doing the application of the Coulombs Law, okay? Now let's get started. Reminding you guys that I'm working from the Oxford Successful textbook. So if you do have the textbook, that is great. And if you have any other textbook that is CAPS approved, that's a textbook that you guys can use. And if you need more textbooks, you can go on Snaplify. Snaplify is an application where you can download all textbooks that you need and absolutely free until the 31st of December 2020. Due to the COVID-19, they've made it, they've graciously made them free for the rest of the year. So you can take advantage and get yourself some textbooks before they expire, and you can find different points of view. But I've noticed that you can't really find the Oxford Successful textbook there, but there's many other textbooks that are good and are CAPS approved and are good for studying and have good information. Okay, so reminding you guys again that in this classroom, we work through the chat. So if there's something that you do not understand, you can just send me a chat and I'll go back and try and explain it to you guys. So it's all about communicating. And please, guys, do not sit while you have something that you don't understand. This is a classroom. What's more important is for you guys to understand the work, not okay, it is to complete the syllabus, but understanding comes first. So you need to make sure that whatever we are doing, you understand and you know what we're talking about. So if you don't, just stop me and ask me and I will go back and try and explain it to you guys. Okay. And also reminding you guys that this year there's only going to be one examination paper for grade 11. I think it's going to be 80 physics and 70 chemistry. So beware of that. We're going to be doing it like that for this year. There's not going to be two papers, and the what you call the I'm just trying to move on to the next slide. Okay, so as you can see there, all the calculations for electromagnetism have been removed. All the other ones are still there, so we still have to do them. And what you're not going to write about is the chemical change. Chemical systems have been completely removed from the syllabus as well. So you're not going to be doing them for this year, but maybe for next year you might have to do them. But for this year, everything has been cleared. Okay. So let's get started. Let's do some electrostatics. Okay. So we're going to be doing the Coulombs law today. So the Coulombs law states that the forces that two charges at rest exert on each other is directly proportional to the product of the charges and inversely proportional to the square distance between them. Okay, hope you guys still remember this from the theory that we did earlier on. This is exactly what has been described as the Coulombs law. Okay, so charges at rest exert forces between each other are directly proportional to the and inversely proportional to the square distance between them. So what we need to know in this part is that, or just a brief reminder, is that we know that when two opposite charges are placed together at a point each charge, they will attract each other. Meaning this charge will excite electric field, so it will be like sort of a motional thing that way goes from positive to negative. But with these ones, they will attract each other. So meaning these two positive, this one will go this way and this one will go that way, and they will never combine together. Okay. So there is our equation right there, which says the force is equals to the Coulombs constant times the charges, which is charge 1 plus charge 2, divided by the distance between them. Okay. So that's how we calculate the force for the Coulombs law. I hope that everybody understands. So the force is equals to the two charges and divided by the square distance. So basically, Coulombs law states. Okay, there we go again, and we have it there. It says states that the magnitude of the electrostatic force between 2-point charges is directly proportional to the product of the magnitude of the charges, which is this Q1 and Q2, and inversely proportional to the square distance between them. So this is the inverse proportionality. Okay, so the proportionality constant is called the electrostatic constant or the Coulombs constant, and has a value of 9 times 10 to the power of 9 nm squared c minus 1 in free space. Okay, so those are important information that you must know, because you will need the K in all your calculations. So you must know that it's always constant. Okay. So now we talk about the Coulombs law. The Coulombs law to Newton's universal law of gravitation, right? And what does it say? It says in this case, M1 and M2 are the masses of the 2-point-like particles, and D is the distance between them, and G is the gravitational constant. So both are inverse laws if you check them, between the gravitational universal law of gravitation and the Coulombs law of forces. Okay. So both laws represent the force exerted by particles, point masses, or point charges on each other that interact by means. Okay, I hope that makes sense. So applying the Coulombs law, the force on each other. Okay, so to calculate this force, at first we need to decide whether the force on the charge is attraction or repulsion. Okay, what does attraction or repulsion mean in this case? We go back to theory. The theory states that when two like charges are placed together and exert force on each other, they become repulsive. But two unlike charges, which means a negative charge and a positive charge, they will be attractive to each other. Okay, so this is how we decide whether the forces on the charges is attraction or repulsion. That's what they want. That's what that means. And then on number 2, we need to draw a free body diagram of the electrostatic force on each sphere. Okay, so we will draw, but you'll see once we start doing examples, we're going to do the free body diagrams of the electrostatic forces on each sphere. On number 3, we use the equation for Coulombs law to perform the calculation. So you see everything works together. You need to have a proper free body diagram with the correct signs in order for you to be able to have values for your calculations. So it's not necessary to include the signs, negative or positive, in the calculation, as you will already have decided what the direction of the force on each charge is. You will know if this one is negative, or if this one is positive, or if it's going on negative direction or on your positive direction. So if you do, a negative answer indicates attraction and a positive answer indicates repulsion. Okay, so you still need a free body diagram to decide what the actual direction of the force on a charge is. Okay, so now we've got an example right here. This example says, calculate the electrostatic force exerted. Calculate the electrostatic force exerted on the 4 nanocoulomb charge in figure 1. Okay, so this is our figure right there. So this one, it says exerted on the plus 1 charge. So they want to know the other one is 3.5 nanocoulomb. And then the distance between the two charges, that is 70 millimeters. Okay, so this is an insulator stand. So this is a two charge conducting spheres on an insulating stand. Okay, so but make sure that here we always convert it to meters. Always convert this to meters. Okay, and then this one is power of 9c. Okay, so the first part is we draw the direction of forces. Remember, both positive. This one is a positive force, this is a positive charge, and this is a positive charge. So what does that mean? These are like charges be going in opposite directional flow in together. So this one will be going this way, and this one will be going the opposite way. Hence, you see the diagram is showing the direction of the forces going in opposite directions. Okay, and this is your distance between them, and this is, you need to state your charges as well. I need to state which one is your positive direction. Okay, so now that we have our force diagram, now that we have our diagram, now we can go back to our equation to try and calculate what we're looking for. And remember, we've got our constant as well. Our constant is the one that it's always the same. It's always constant. It's 9 times 10 to the power of 9. Okay. So here we are. Now we go back to the equation, which is F is equals to KQ1 Q2 over R squared. And now you've plotted everything in your equation. All you're given are plotted in the equation. You see, here it's 10 to the power of, it's 4 times 10 to the power of minus 9 because of the nano. Because it's written nano, it's to the power of 10 to the power of negative 9 for each. And you calculate, and this is your answer. So your answer is the force on the 4 into nanocoulomb charge is 2 times 10 to the power times 10 to the power of minus 5 Newton to the left. Okay, and left is this way. Why do we say left? Because they wanted to know the force exerted on this one. Okay, guys, I hope that this makes to you. But so the superposition of forces. We often hear charges that exert force on each other. So that's what we've been working with basically in this chapter. So these forces superpose. Therefore, we use vector addition to find the force on a particular charge. The figure below shows three charges that all force on each other. Okay. They're all exerting for Q2, and you've got your Q3, and forces pulsive forces. Okay. And I hope that it open up your mind on basically what is going on here. So if you have three charges, to calculate the net force F net that acts on a particular charge, this is the steps that you have to take. Number one, you need to decide which is the positive direction to show it on your force diagram. Decide on the charge. Number three, on number four, calculate the magnitude and F1 plus F2 plus F3. So here is, we've got an example. It says here, calculate the electrostatic force that acts on a charge Q2 in the figure that we did here, which is this figure right here, Q2, as a result of the electrostatic forces exerted by Q1 and Q3. Okay. So how are we going to do this? To draw our free body diagram. Okay, I'm just trying to get to the okay. Sorry about that. But guys, you need to pay proper attention here because this work is very complex, especially the started by doing the theory. The theory part. Okay. So we're going to draw our diagram. Oh, sorry about that. We had a bit of a connection problem, but I hope that we are still together on this problem. Okay. So for step one, we need to draw the diagrams, right? So remember, the diagrams are the ones we're taking it from the question, and we're taking it from this point. Okay. So basically, we're working with Q2. So they want to know the distance between Q1 and Q2 and between Q3 and Q2 again. Okay, so that's why in this case, those are the distance that we're working with, right? Those are the two distances that we are working with. So it's going to come here, distance between Q1 and Q2 will be 100 millimeters. And where do we get the 100 millimeters from? It's from here. From Q1 to Q2, it's 100 millimeters. From Q3 to Q2 again, it's going to be 80 millimeters. Okay. So the next one, we need to calculate the magnitude of and direction of each force. So now we're going to first start with the direction from Q1 on Q2. Okay, so that's going to be the constant. We're going to have our two Q's like they're given on them. It's going to be 9 and 4, right? It's the ones according to this one. Because we're doing Q1 and Q2, Q1 and Q2, it's going to be 0.05 and 0.1, okay? Times 10 to the power of minus 6 of each, okay? And we have our constant and we have our distance, which is a 100 millimeters, which is 0.1 meters. And this is going to be the answer for the force from Q1 on Q2 is going to be 4.5 times 10 to the power minus 3 to the left, okay? To the left. And why is it to the left? Q1 to Q2 to the left because it's going this way, okay? Okay, and now we move. So on the next one, we do the same procedure, but in this case, we're using Q2 and Q3. When we do Q2 and Q3, we divide it by the distance, which was 80 millimeters, remember? This one right here. And we divide them both, and we're going to have our answer once again. Because remember, this is a positive direction, and these are the negative direction. And we said if our forces in there, you can see it's moving to the left. So it's going to be 5.63 times 10 to the power of minus 3 Newton to the left. Okay. So now, after that, because here they said you must calculate the net electrostatic force that acts on charge 2, now we need to calculate the net force. Okay. So we're taking the right as positive. The right is positive, as we've already mentioned it on our force diagram. It means the left is negative. So in this case, it's going to be minus of each, and our net force is going to be a negative. So the answer is that the net force on Q2 is 1.013 times 10 to the power of minus 3 Newton to the left. Okay. I hope we are good and you understand it. It's not so difficult, guys. It's just a matter of understanding the concept, which force is acting on which one, and from there you get to start calculating each individual forces that act on a particular force. Okay. And then now we move to forces that act in two dimension on a charge. So they say here, when three charges are arranged in a right angled formation, to calculate the force on the charge position at the corner, number one, you need to decide on the X and the Y direction. Number two, you need to decide the direction of each force that acts on the charge. Okay, so the direction you must know, if this one is positive, this one is negative, etc. Number four, you need to calculate the magnitude and direction of each force that acts on the charge. So here we work with forces, okay? And number five, you need to draw the diagram of Rx, Ry, and R resultant. So it's going to be Rx, Ry, and we need to have a resultant force right here, okay? So we use the Pythagoras and trigonometry to calculate the net force. So which means in this case, our net force is going to be the R hypotenuse right here. Okay, so let's see how we can do a problem like that. Okay, so it says here, it says here, draw the diagram. Number one, you draw the diagram to show the force, right? You need to choose Q1 and Q2 right here. So we've got one that acts on, which this way. So this is show. This is our x-axis, this is our y-axis. But if you check here, this one is on a negative side, right? And this one, the y positive direction. Okay, I hope that you guys can all hear me properly. So now this is relative to Q2. And Rx is on the direction. If it was this way, it would be positive, but it's this way, it's negative. And this one, the y-axis is on a positive direction. If it was facing downwards, it would be a negative direction. Okay. So now we calculate our Rx. Our Rx is equals to Q1 on Q2. Q1 on Q2. And that will give us this formula, and we've got our constant, so we use what is given, the 28 times 10 to the power of minus 9 times 32 times 10 to the power of 9 is divided by the distance, which is this one that we have here of 0.03 meters. And then we do the same thing for our y-axis. Okay, so we do our y component now, and that's going to be the Q3 on Q2, and that's going to be K is equals to Q2 Q3 divided by R squared, and this is what it's going to give us. We're going to calculate, we're going to put the individual forces, and never forget the constant, guys. The constant, without the constant, your answer is absolutely wrong. Okay, then we have our r-axis, our y-axis in the positive y direction, so it's all in this direction. Okay, so now we still need to find the resultant. So now we can draw our diagram of rx, which is this one, and ry. So now we're looking for the resultant force between them, right? So this here will be our resultant force. So let's calculate the resultant force of F net. And that is going to be F net squared is equals to R squared is equals to R squared Y, R squared X. So this is going to, the minus here is going to cancel out the direction. Okay, so 1 Newton. Okay, so now moving on, because don't forget here we took a square root, because here it became a root because the r was also squared, right? So after this you put a square root and you got this. Okay, so from there we move on to calculate the direction of F net using trigonometry. Okay, So if we have a triangle like this, trigonometry, we're going to say tan theta is equals to Fy minus Fx over Fx, right? We're using the tan equation, right? And we're going to have this, and our theta is going to be um, second function tan. I don't know how you put it in your calculator, but is that shift tan, which is the tan minus 1 um, of this one, and it's going to give you 35 degrees, and you're going to minus that with 180, because this one, you see where it is, it's right here. We are looking for this direction from here to here, but we just calculated this one here. Okay, we calculated this one here, and we need to minus it by 180 to get this whole thing from x to the resultant. Okay, so which means that the net force that acts on Q2 is 0.011 Newton. Direction is 144.13 degrees anti-clockwise from positive x direction. Okay, I know it was quite a challenging question, but I hope that you guys understand it. Okay, let's do one more question. Oh, it's quite long. And just before we get to close classroom, and I can give you a homework. So it says here, 2-point-like charges carrying 3 times 10 to the power of 9 and 5 times 10 to the power of 9 are 2 meters apart. Determine the magnitude of the force between them and state whether it is attractive or repulsive. So we already know the answer to attractive or repulsive. This one is positive and this is force. Okay, so the force will be attractive. So we point charges, and we use a column, but due to your column constant, which is this one here. Okay, so we are given all of this. So we can draw our force free body diagram. Will show the force directions. It is always moving to the hand side, and the positive is always moving to the right hand side. Okay, so this is our 2 meters, guys. Please don't forget to draw your free body diagram all the time. It's very important. And therefore, now you can place your information into your equation. And this is what we will get from our answer. So thus the magnitude of force is 3.37 times 10 to the power of 8. However, since the point charges have opposite signs, the force will be attractive. Okay, so it's not moving on one direction. So we don't need a direction because they are both opposite. They both attract each other. If they were both negative, there would be a direction that we'd have to know that on the right, on the positive direction or on the negative direction. Okay, so we can draw the free body diagram to show the forces. Each charge experiences force with the same magnitude, and the forces are attractive. So you can write something like this. Who knows? Maybe you might get some extra marks for this. Okay, so now we're coming to the homework. Please, guys, let us do our homework. Our homework is most important. Homework. Please take a screen grab of this page, and this is going to be the homework for Monday. So make sure that you've got it and you've done it. Okay, and this is the rest of it, guys. Please do all of it. Do all your homework. Okay, and then we'll do the corrections on Monday. Guys, this is still revision work. Remember, we're going to have assessment too. And our little assessment is going to be you trusting yourself to do the right thing by testing yourself. And if you test yourself, you'll know what you know and what you don't. And that's the most important part of learning. Okay? So this is the solution for the first one, just to give you a start on doing your problems. It will be this. It's also very self-explanatory. It's going to be, it's given two charges and separated by distance. But this one, you see, this is a repulsive force because these are like charges. So they are moving on. Because remember when we work with ions, magnitude, we always state of positive in the section. Okay, next, physical sciences grade 11 problems. Then goodbye.